Hey guys, Jay Keast here, and I want to work one more example with you dealing with our concentric spherical conductors. Try saying that 5 times fast. But I want to do one where my inner sphere has a charge 2q, and as does my outer sphere. In other words, they both are going to have the same overall charge. Okay, so let's start by, and again, they're both conductors. So let's start by talking about what's happening to this outer shell. Because it's a conductor, it's got an overall charge of positive 2q. But inside, I've got this positive 2q. So I'm going to induce on this inner surface here a negative 2q of charge. Now, because it needs an overall plus 2q, this is overall, or net. On this outer surface, there needs to be a positive 4q. Now, if we're talking about the electric field for when R is less than A, I'm inside this conducting sphere. And we know that conducting spheres, all of the charge is located on the outer surface. They have an equipotential surface. So there's no potential difference anywhere across the surface of a conductor. So for R is less than A, or inside this conductor, I have no electric field because we are going to be using Gauss's law. And because of that, there is no Q enclosed because all of the charge is on the outside. My Gaussian surface, keeping with the blue here, my Gaussian surface would be inside, enclosing no charge. Now, this region of space out here, if I make my Gaussian surface somewhere in this empty region of space, in other words, for R in between A and B, well, now I have an electric field. And my Q enclosed is going to be 2Q because I'm enclosing all of this charge. So this would be no different than the electric field of a point charge. So my total charge enclosed would be 2q over 4 pi r squared epsilon naught. Then my next region of space would be inside this conductor. And again, my q enclosed would be 0 because I would be enclosing the negative 2q and the positive 2q. So for that region, for R in between C and B, my electric field is 0. Then once I get outside of the sphere, in other words for R greater than C, well, now I'm enclosing the entire charge of this whole thing. So I've got a charge of 2q and then an overall charge of 2q again on the outer surface, giving me a total q enclosed of 4q. So my electric field outside of this whole system would be 4q over 4 pi r squared epsilon naught. 4's canceling, giving me a total charge of q over pi r squared epsilon naught. I could also do some canceling over here, but that's not important. Now, let's talk about the potential, the electric potential or the voltage. And let's start with the voltage outside of the sphere. So with that, if I start with the electric potential outside of the sphere, I'm dealing with this electric field over here. So for the voltage, I'm going to be going from some infinite distance out to a point, let's just say right here. And I'm bringing a positive test charge from infinity out to this point. So I can utilize this equation, minus VB equals the negative integral of infinity to some distance r of my electric field dotted with dl. Now, I know my electric field for outside, it's this right here. All of this is a constant. VB is for r equals infinity. That just becomes 0. And all of this simplifies down to, when we're talking about r greater than c, that is going to equal, let's go ahead and just cancel our 4's. It's going to be q over pi r epsilon naught. Okay? Now, once I pass this outer surface here and I get inside the conductor, yeah, I've got no electric field, but I would be integrating 0 dr. Okay? And my electric potential inside this outer shell here, inside the conductor, would actually be a constant. And the constant it would be I plug in C for my R. So my electric field inside this conductor here, it's going to be a constant, and it's going to be Q over pi C epsilon naught. And it's going to be that for this entire surface. So the potential on this side is going to be the same right up until I get to that point. Okay? So my potential at B is going to be that. Okay? Now, if I wanted to make a graph of potential versus distance for something like this, it would look like so. So let's say I'm going to graph potential, start at 0, go to A, go to B, and then go to C. Beyond C, I've got my potential over here being equal to 4 pi, oh, excuse me. Oh, that looks bad. It was equal to Q over pi R epsilon naught. So this function is going to look or appear to be proportional to just 1 over R. So I'm going to draw it kind of like that. Okay. Then in the section from B to C, it is a constant. And so it is going to be flat like that. Then in the region of space between the two capacitors, or excuse me, well, this is a capacitor, but in between my two conductors, I've got potential again. And it's going to again be proportional to 1 over R. And because these charges are the same on both conductors, this is actually going to be a fairly smooth, oops.
Students and teachers, part of this interruption, please
Really?
excuse the A.M. Francis Tuttle students. They had some difficulties with their bus today and are just now arriving. Again, please excuse the Francis Tuttle A.M. students. They're just now arriving to class. Thank you.
One of the disadvantages of making a video tutorial in the classroom. So, again, this is in between my two conductors. So I have a 1 over R function, and it connects to that constant, and then I have a 1 over R function again. Then from 0 to A, I'm inside another conductor. So my potential is going to be a constant again. Because they are like charges, this graph is actually going to be very smooth. It's going to be a continuous graph. Anytime you have a flat line, we are inside the conductor. Therefore, our potential in these regions is constant. Anytime we are concave, we are in the region of space either outside of the entire assembly, right here, or right here, we are in between the two conductors. Now, what would the electric field look like if I graphed that versus distance? So again, starting at 0, A, B, C, and then beyond. Okay. Well, I know that for inside the conductor from 0 to A, I have no electric potential. And that's also going to be true from B to C. Again, not having any potential. From A to B, my electric field was proportional to 1 over R squared. So I'm going to draw something that looks like that. Now, beyond C, we had an electric field that was proportional to 1 over R squared, but we had a larger electric potential, meaning that I would need to draw that graph starting higher up, indicating that I have a higher electric field outside of the entire assembly, because remember, when we were outside of the entire thing, we were enclosing a charge 4Q as opposed to a charge 2Q. Okay, so that's a brief video tutorial for electric field when we're dealing with concentric conductors.